particular number was established in 1922, and for more than 80 years, it remained the undisputed peak, 32.8 degrees Celsius. This was the warmest temperature ever recorded in the United Kingdom during the month of May. First measured in London's Camden Square, that exact figure was recorded once more in 1944, but after that, the record held firm for generations. Then, on Monday, the 25th of May, 2026, that fixture was dislodged. The reading at Heathrow reached 33.5 degrees Celsius, establishing a new high for the hottest May day in the nation's history. A barrier that had stood for over 8 decades was not gently pushed aside. It was decisively shattered, vaulted over, by the better part of a full degree on a spring bank holiday the British more commonly associate with rain. The daytime record was extraordinary, but a second number from that same heat event is, in some respects, even more frightening to meteorologists. On one of those nights, the temperature at a small aerodrome called Kenley Airfield only fell to 19.4 degrees Celsius. It was the warmest May night ever recorded in the United Kingdom. This matters because the night is when the body gets a chance to shed the thermal load it has carried since morning. This nightly recovery is a biological necessity. A night that never cools is a night where that reset button has been effectively removed. A record-breaking day is a headline. A record-breaking night is a quieter, more insidious threat. If this were the complete picture, it would already be a significant event, but the full story is stranger and far larger. As that record was being set in Britain, nearly the entire western portion of Europe was sweltering. Temperatures in Spain approached 101 degrees Fahrenheit, while thousands of miles away, a separate and even more brutal heatwave was claiming lives across the plains of northern India. 3 distinct regions of the Northern Hemisphere, with no direct geographical connection, were all burning simultaneously. These events are not a matter of coincidence. They are linked by a single, invisible structure, a physical phenomenon moving 7 miles above our heads that most people have never even heard of. There is something profound in the fact that a record speaking to the shifting behavior of the entire Northern Hemisphere was set not at a remote desert observatory, but on the tarmac of a major international airport. The grand patterns of the atmosphere do not always announce themselves with grand drama. Sometimes they reveal themselves in the temperature reading at Heathrow on a Monday, in ordinary corners of southeastern England where people live their lives. We must learn to read these small local data points as the visible edge of something truly vast. The narrative of this extraordinary event, it seemed, was far from over. After that Monday, the Met Office anticipated that the heat would intensify further, with a peak temperature near 35 degrees Celsius forecast for parts of London and the home counties. To truly grasp what is unfolding with our weather, we invite you to join us at Calm Space on a journey of discovery. We're going to follow this thread all the way up to the atmospheric layers where the weather is truly decided. By July, this will be the story everyone is talking about. Forecasts for Tuesday showed temperatures climbing above 30 degrees Celsius across eastern Wales and much of southern and central England. Yet, just as swiftly, the projections showed the warmth dissipating. 31, then 30, then 27, then 28. Within a few days, the familiar temperate air would return. It is worth reflecting on how this rapid rise and fall would have felt to someone living through it. For most people in Britain, the heat arrived, crested, and then receded over a long weekend and the days that followed, allowing life to settle back into its famously mild, grey normal. A week later, it would have been easy to misremember the event, filing it away as a pleasantly timed hot spell for the bank holiday. And this is precisely the danger of such an event, in terms of how it is understood. The heat itself is brief, and for many in a prosperous, temperate nation, It is not only survivable, but even enjoyable. The record it sets becomes a single line in a database, while the deeper meaning, the signal about the behavior of the hemisphere, makes no grand announcement before it vanishes. This is why it is so crucial to pause and examine an event like this while the memory is fresh, to pull it apart and understand its mechanics, rather than letting it slide past as just another warm weekend. The weekend fades, but what it revealed should not. The very form of this event is what holds the clues. This was not a prolonged heat wave that lingered for weeks on end. Instead, it was an abrupt spike, a sharp, intense, and short-lived blade of heat that arrived, shattered an 80-year record, and then promptly began to subside. A spike of this nature is telling. It suggests the cause was not a slow, seasonal warming, but something more deliberate, a specific configuration. A particular pattern had formed in the atmosphere, a shape that generated extreme heat for a few days before it started to unravel. This leads us to the central question that this entire exploration seeks to answer. What was this shape? What exactly arranged itself in the skies? And perhaps most importantly, why did this same phenomenon appear over Britain, Spain, and India all at the same time? It is useful to consider why the British case provides such a clear starting point for our investigation. There is a specific reason this country, of all places, makes the atmospheric pattern so legible. Britain is simply not designed for intense heat. While that may sound like a casual remark, it is a statement with significant meteorological weight. The United Kingdom is situated at a latitude that, on other parts of the globe, corresponds to genuinely cold territory. It is only kept temperate by the surrounding ocean and the warm currents bathing its coastlines. Its weather is defined by its maritime climate, a climate of moderation, characterized by overcast skies, gentle rain, and temperatures that seldom venture to extremes. The British summer is renowned, even notorious, for its restraint. Therefore, when a temperature record is broken in Britain, it happens in a place where such heat is an anomaly. The entire built environment, from houses without air conditioning to railways that buckle and asphalt that softens, is calibrated for a much cooler world. A record set here is a record that goes against the very character of the nation, and that is part of what makes the signal it sends so unambiguous. Now, let us consider the human texture of that record-setting day, because the date was not incidental. The 25th of May, 2026, fell on a spring bank holiday, one of the cherished long weekends that dot the British calendar. These weekends are traditionally times of modest national rituals, trips to the coast, visits with family, and barbecues lit in hopeful defiance of a typically drizzly forecast. The bank holiday is, in the collective imagination, a small wager against the notorious unreliability of British weather. On this particular occasion, the wager didn't just succeed, it overshot wildly. Crowds swarmed the beaches, and parks overflowed with people. For a brief moment, the entire nation seemed to adopt the lifestyle of a Mediterranean country. Yet, beneath this pleasant surface, beneath the ice creams and the sunburn, the instruments at Heathrow were quietly logging the hottest May temperature in the whole of British history. This reveals the strange duality of a heat event like this one. For the majority of people experiencing it, it is simply a glorious weekend. The danger, the broken records, and the deeper implications are all invisible in the moment, their significance only becoming clear in retrospect, when the data is analyzed and that single hot weekend is placed in the context of what was happening across the rest of the hemisphere. There is one final observation to make before we ascend into the atmosphere to find our answer. The Met Office, in its description of this British heat, was very careful about a particular point. There is a popular and powerful image of hot weather as an invasion, a blast of desert air, a Saharan blowtorch carried north across the Mediterranean to scorch London. It is a compelling picture, and not entirely without basis, as warm southern air did play a part later in the week. However, the Met Office was clear that this was not the primary driver of the British heat. The main mechanism was something less visually dramatic, but far more crucial to our understanding. It was a great dome of high pressure, building directly over and near the United Kingdom itself. The heat, in other words, was not mostly imported from afar. It was largely manufactured right on the spot. This distinction will become enormously important, as it is the key to the entire mechanism. This is, in fact, the single most common misunderstanding in conventional reporting on heat waves. Pay attention to how heat is typically described on the news. You will hear of hot air being dragged up from Africa, of plumes of warmth surging north, or of the Sahara reaching out a hand. This language portrays heat as a tangible substance, a hot object that exists somewhere else, and is then transported to you, much like a parcel delivered by a courier. It gives the impression that the heat is merely a visitor. But this is not, for the most part, how record-breaking heat of this kind is formed. The heat over Britain was not a thing that travelled. It was a thing that was made locally by the behaviour of the atmosphere, directly overhead. Nobody delivered it. The sky above Britain manufactured it on the spot, out of air that was already there. And the same fundamental principle, in its own way, applies to the events over Spain and France, and in a related manner, over India. Once we realize that extreme heat can be generated on the spot, rather than simply being transported from elsewhere, a great deal of common confusion dissolves. This shift in perspective brings the true question into sharp focus. If the heat is being created locally, then some mechanism within the atmosphere must be responsible for its creation. To grasp how the air itself can manufacture record temperatures without importing them from a desert, we must look upward. We need to ascend far beyond the rooftops and sweltering cities to the very altitude where our weather is truly forged. Roughly 7 miles high, there flows a river of wind, and at this moment, that river is behaving in a most unusual way. High above our heads, at an altitude of 7 miles, a current of air flows in perpetual motion, circling the entire globe. This is the jet stream. It is a vast river of wind, thousands of miles long but only a few hundred miles wide and a couple of miles deep. A thin, swift ribbon wrapped around the Northern Hemisphere. Though invisible and intangible to us on the ground, it is one of the most powerful forces governing our daily weather. Most people know the jet stream only in the context of aviation, as the current that makes a flight from New York to London faster than the return journey. But this understanding barely scratches the surface. The jet stream is far more than an aerial convenience. For the planet's middle latitudes, it is the master controller of weather. It directs the paths of storms, separates vast air masses, and ultimately determines whether our days are warm or cool, rainy or dry. For anyone living in the temperate zones of Europe, North America, or Asia, the jet stream is the most significant atmospheric feature above you, yet it remains largely unconsidered. To comprehend what unfolded in late May, we must now examine this river of wind, and in doing so, we may forever change how we interpret the weather. The existence of the jet stream can be traced back to a simple, fundamental imbalance on our planet. The equator receives intense heat while the poles remain cold, and the atmosphere is in a constant effort to equalize this thermal difference by moving warmth from the tropics toward the Arctic. This process, however, does not unfold in a straight line. Because our planet is spinning, the flow of air is deflected from its direct south to north path. The Earth's rotation bends this movement, turning it until it races not toward the pole, but eastward. The result is a high-altitude wind tearing around the globe from west to east at speeds that can surpass 100 miles per hour. This is the jet stream, a physical manifestation of planetary physics. In essence, the jet stream acts as a boundary line, separating the cold air of the north from the warmer air masses to the south. It is the great fence between two distinct temperature worlds. But it is crucial to understand that this fence is not straight. It was never meant to be. The jet stream does not encircle the planet in a perfect, compass-drawn circle. Instead, it meanders, wandering north and south as it travels. It traces out enormous, slow-moving curves, great looping waves that can span 1,000 miles or more, from one crest to the next. These atmospheric waves are known as Rossby waves, named for the scientist who first described them, and their presence is a normal, permanent, and healthy feature of our atmosphere. The jet stream has always had these waves. Some weeks, these waves are small and gentle, allowing the jet stream to flow in a relatively tidy and fast line. In other weeks, the waves grow large and dramatic, with the current swinging far to the north in one region and plunging deep to the south in another. It is the size and speed of these very waves that determine the kind of weather you experience on the ground. Imagine the jet stream as a winding river viewed from high above. Where this river bends far to the north, it carries the atmospheric boundary with it, allowing a great bulge of warm southern air to sit underneath that loop. Conversely, where the river dips far to the south, it drags cold, northern air down with it, causing the land below to become cool and unsettled. Therefore, the position of these loops directly corresponds to your local weather. A northward loop above you brings warmth, while a southward loop brings cooler temperatures and often rain. In this way, the jet stream is not just a current of wind, it is a template, a stencil that paints the weather onto the surface of the planet. Under normal circumstances, this atmospheric stencil is constantly in motion. The waves of the jet stream are not static, they drift slowly from west to east. This means the entire pattern progresses across the globe, so a warm bulge that was situated over your region on a Monday will have slid eastward by Thursday, bringing its weather to someone else. As it moves on, a new part of the pattern, and thus a new type of weather, moves in to take its place. This steady movement is what we experience as the ordinary churn of weather. A few warm days, followed by a front, perhaps some rain, then a cool spell, and then warmth once more. The pattern progresses, the stencil slides along, and nothing remains fixed for too long. But what happens when this natural progression ceases? Sometimes, the waves of the jet stream stop sliding. They can grow so large, so exaggerated, and steeply curved that they lose their ability to travel eastward. A small ripple in the flow moves along with ease, but a vast, towering, looping wave is heavy and sluggish, and can grind to a complete halt. When this occurs, the entire atmospheric pattern becomes locked in place. The warm bulge that was supposed to move on instead remains stationary day after day. The stencil stops sliding, and whatever weather it was painting onto the land below gets painted over and over again in the same location. Meteorologists have a specific name for this stalled, locked, and exaggerated state. They call it a blocking pattern. This phenomenon occurs when the jet stream, in effect, blocks its own path, and in late May of 2026, the jet stream over the North Atlantic and Europe did precisely this. It entered what is known as a strongly amplified, slow-moving, blocked configuration. The atmospheric waves grew to an immense size, and then they simply stopped moving. This was not a minor fluctuation. It was a profound shift in the atmospheric machinery. There is a reason the word block is so fitting, and it helps to visualize the process. In ordinary weather, we see a parade of systems moving through. A low-pressure system, a band of rain, a period of clear skies, a warm spell, all shuffling along from west to east. Each weather system takes its turn over a region and then moves on to affect another area. A blocking pattern, however, is what happens when one massive, immovable feature plants itself in the middle of that parade and refuses to budge. It is like a boulder suddenly dropped into the marching line, bringing the entire procession to a standstill. Under normal conditions, weather patterns are in constant motion. But when the atmosphere's natural circulation is obstructed, everything changes. Any system that should have passed through the area is now forced to circumnavigate it. Storms are diverted, pushed far to the north or south, embarking on long, unconventional detours. Beneath this atmospheric obstruction, or block, the existing weather becomes frozen in place. This happens because the very mechanism that would typically sweep it away has been effectively disabled. Such a block doesn't merely create a single zone of stagnant weather. Its influence disrupts the atmospheric flow for thousands of miles in all directions. It is, in fact, the most profoundly disruptive event the mid-latitude atmosphere regularly inflicts upon itself. It is worth pausing on this point, because the notion of a wave that simply stops moving can feel deeply counterintuitive. Yet, this very concept is the cornerstone of our entire story. We are accustomed to waves that travel a swell on the ocean rolling toward the coast, or ripples expanding across a pond. The waves in the jet stream typically behave this way, as traveling features sliding steadily from west to east. But the atmosphere is not water, and its waves are governed by far more complex principles. A Rossby wave, as these atmospheric waves are known, possesses a natural relationship between its dimensions and its velocity. Smaller, more compact waves are agile, tending to race eastward. In contrast, the large, broad, deeply curved waves are sluggish. The very largest among them can slow to a near standstill, and in some cases, even drift backward toward the west, against the prevailing flow. So, when the atmosphere amplifies its waves, stretching them vertically and horizontally, it is doing more than just creating more extreme weather. It is also making that weather slower, causing it to linger. The amplification and the stalling are two sides of the same phenomenon. A jet stream with immense waves is almost by definition a jet stream with slow or stationary waves. This is the profound reason a blocking pattern is so perilous. It doesn't just generate extreme conditions. It produces them and then holds them captive. There is also a hidden feedback mechanism within this process, a way the block reinforces its own existence, which helps explain why these patterns can be so stubbornly persistent. Once a powerful ridge of high pressure establishes itself, it begins to deflect the jet stream around its perimeter. It acts much like a large boulder in a river, compelling the current to split and flow around it. The jet stream, forced to detour around this established ridge, ends up reinforcing the very shape that is diverting it in the first place. The pattern, in effect, carves its own groove in the atmosphere and then settles more deeply into it. When forecasters observe a strong block developing, they know it is not a transient feature that will dissipate in a day or two. It has a kind of inertia and architectural stability, and it will hold its ground until a force large enough to dismantle it comes along. This is why the heat beneath a block is never a brief affair. It is a siege. The pattern locks into place and then holds the line, day after relentless day, as the heat on the ground below continues to build. One particular type of blocking pattern is worth visualizing, as it was the one at play in this event, and its name perfectly describes its form. It is known as an omega block. The name is derived from the Greek letter omega, which resembles a horseshoe or a grand, rounded arch supported by two small feet. If you can picture that letter, you can imagine the path of the jet stream. It comes racing in from the west, but instead of continuing in a straight line, it swings sharply upward, climbing far to the north in a great, rounded arc. At the crest of this arch, it curls over and then plunges back down the other side, dipping far to the south before it can finally resume its eastward journey. That central arch, the large, rounded hump in the jet stream's path, corresponds to a ridge of high pressure. Meanwhile, the 2 feet at the bottom, the 2 points where the jet stream has plunged southward, are troughs of low pressure. An omega block is one of the most stable and unyielding patterns the atmosphere can create. The high-pressure ridge in the center is effectively locked in place, pinned by the two flanking low-pressure troughs which act like bookends. With this structure established, nothing can move. The entire configuration can remain nearly motionless for many days, sometimes for more than a week. And the land that has the misfortune of being situated under that central arch, under the high-pressure ridge at the top of the omega, is subjected to relentless heat. This isn't just for a day, it lasts for as long as the block holds. This is the very shape we were searching for, the atmospheric configuration responsible for the crisis. When the United Kingdom's temperature record was broken at Heathrow, when Spain reached 38 degrees Celsius, and when the western flank of an entire continent baked in unison during the same week, it was all because the jet stream had drawn a colossal omega in the sky above Europe. The western nations of the continent were positioned directly beneath the top of that arch. It is important to state clearly that, as a phenomenon, there is nothing inherently exotic or unprecedented about an omega block. Meteorologists see them on their charts regularly. They are well-recognized patterns with established names and understood behaviors. An omega block is part of the normal vocabulary of the atmosphere, much like a specific chord is part of the normal vocabulary of music. It is not a glitch, nor is it a sign that the sky is broken. The atmosphere has been drawing omegas for as long as it has existed, and most of the time, an omega block can be a rather pleasant occurrence. A stable ridge of high pressure in the right season and over the right location simply translates to a long stretch of calm, clear, and sunny weather, the kind of settled spell that people often enjoy. The danger, then, is not in the existence of the pattern itself. The danger lies in the details. It is a matter of when the omega forms, where it sets up, how intense it becomes, and how long it persists. An omega block, situated over a cool region during a mild season, might result in a beautiful week. But the very same pattern, parked over a continent already primed for heat, and in a configuration of near-record strength, becomes the engine that shatters an 80-year record. It is the same atmospheric chord played in a different context, yielding a wildly different and far more dangerous consequence. However, simply naming the shape is not the same as truly understanding the process. Knowing that a ridge of high pressure was parked overhead tells us where the heat was concentrated, but it does not yet explain why high pressure generates heat in the first place. A ridge of high pressure does not become warm because warmth was delivered to it from afar. As the Met Office noted regarding Britain, the extreme heat was not primarily imported from the Sahara. It was manufactured locally. So, this leads us to the critical question. How does a stationary dome of high pressure sitting still in the sky manufacture record-breaking heat from the air that is already there? To answer that, we must look inside the dome and understand what the air itself is actually doing, and what it is doing is falling. Part 3. How a dome builds its own heat. To grasp how a heat dome can bake the landscape beneath it, we must first appreciate a fascinating and somewhat counterintuitive property of air. When air is compressed, when it is squeezed into a smaller space, it heats up. Conversely, when air is allowed to expand, it cools down. This simple relationship between pressure and temperature is one of the most fundamental, yet often overlooked principles in everyday science. It works quietly all around us, explaining why the air grows colder as you ascend a mountain, even as you move closer to the sun. The air at higher altitudes is under less pressure, so it expands and cools. It is the reason a diesel engine can ignite fuel without a spark plug, using only the intense heat generated by compressing air within its cylinders. This same principle is the foundation for refrigerators and air conditioners. And, as we will see, it is the hidden engine that powers a heat dome. You have likely experienced both sides of this phenomenon without giving it much thought. If you have ever used a hand pump to inflate a bicycle tire, you may have noticed the base of the pump becoming warm, sometimes surprisingly so. That warmth is a direct result of your effort, generated by the act of compressing air inside the pump. The reverse is also true. Take any aerosol can, such as deodorant or spray paint, and hold down the nozzle for several seconds. The can will grow cold in your hand. As the pressurized gas rushes out, it expands rapidly, and this expansion draws heat from its surroundings, chilling the can. This is not some peculiar quirk of pumps and spray cans. It is a basic law governing the behavior of all gases, including the vast expanse of Earth's atmosphere. Now, let us elevate this concept into the sky, into the very heart of a high-pressure system. The defining characteristic of a high-pressure zone is a vast region where air is slowly but relentlessly sinking from the upper atmosphere toward the ground. This descent is not a dramatic plunge, but a gentle, persistent subsidence that can span an enormous area and continue for as long as the weather system remains in place. It is a process that sets the stage for a powerful transformation. And here, in this slow descent, we find the engine of the heat dome. As the column of air sinks, it moves into the thicker, denser layers of the atmosphere closer to the surface. The pressure exerted by the air below it steadily increases. Consequently, the sinking air is squeezed and compressed by the growing weight of the atmosphere it is descending into. Just like the air inside the bicycle pump, this compressed air gets hot. The air within a high-pressure dome warms up. Not because it has been transported from a distant desert, but simply and purely because it is being compressed on its downward journey. The dome generates its own heat through the physical act of making the air fall. The high-pressure ridge that the jet stream held stationary over Western Europe was a perfect illustration of this mechanism. Every hour of every day that it persisted, it was gently forcing a continent-sized mass of air downward. This downward motion compressed the air, and that compression, in turn, warmed it. A heat dome does not need to import warmth. It manufactures it continuously from the simple downward movement of the atmosphere. This is precisely what the Met Office described when it stated the British heatwave was driven by high-pressure building over the region rather than by hot air arriving from the Sahara. The heat was being created on site. The dome was its own furnace. However, sinking, compressing air has another consequence, one that is just as important as the first. As air descends and warms, its relative humidity plummets, which makes it extremely difficult for clouds to form. In fact, this sinking air actively works to destroy clouds, causing them to evaporate. The result is that underneath a strong high-pressure dome, the sky tends to be not just warm, but persistently clear and cloudless. The atmospheric conditions themselves conspire to keep the skies wide open. Think for a moment about what this means for the ground below. Day after day, with the clouds wiped away, there is nothing to shield the land from the sun. Each morning, the sun rises into an empty sky and pours its full, undiluted energy directly onto the surface. With no cloud cover to reflect a portion of this energy back into space, the land absorbs nearly all of it. The soil heats up, as do the pavement, the rooftops, and the fields. And because the high-pressure dome is locked in place, this intense solar baking is repeated on the very same patch of ground the next day and the day after that. This effect is especially pronounced in cities, which have their own unique ways of intensifying a heat dome's work. A city is constructed from materials that seem almost designed to absorb and retain heat: asphalt, concrete, brick, and dark roofing. These surfaces soak up the sun's energy throughout the long, cloudless day and then radiate it back out slowly during the night. This is a major reason why nighttime temperatures in a city remain higher than in the surrounding countryside. When you add the waste heat generated by the city itself, from engines, machinery, and air conditioners pumping hot air out of buildings, you create an environment that struggles to cool down even long after sunset. When a heat dome settles over a city, its relentless daytime baking is amplified by the city's own heat-hoarding nature. It is no coincidence that the record temperature at Heathrow was set on the edge of one of Europe's largest urban areas. The city did not cause the heat dome, but it was a willing partner in pushing the temperature to its extreme. This is where the effects begin to compound, creating a dangerous feedback loop that can cause temperatures to run away. As the relentless sun bakes the ground day after day, the soil dries out. This is a critical problem because moist soil possesses a form of natural air conditioning. When sunlight hits damp ground, a significant portion of its energy is used to evaporate the moisture, turning liquid water into vapor. This process of evaporation consumes energy without significantly raising the temperature, much like how sweating cools your body. But once the soil has been baked completely dry, that safety valve is gone. With no more moisture to evaporate, all of the sun's incoming energy goes directly into raising the temperature of the ground. As a result, the ground gets hotter, faster, and so does the air directly above it. The heating process begins to accelerate, creating an ever-worsening cycle. A heat dome, lingering for days, enters into a dangerous partnership with the ground below. When the land loses its ability to cool itself, the dome and the parched earth begin to feed one another, causing temperatures to climb relentlessly. This cumulative effect is key to understanding a common puzzle about heat waves. Many people assume the hottest day should be the first, but under a heat dome, the opposite is true. It does not arrive at its peak intensity. It establishes itself and then builds. The first day under a new high-pressure ridge might feel pleasantly warm. The second day is warmer. By the fourth or fifth day, the soil has dried, disabling the natural safety valve of evaporation. Accumulated solar energy piles up in the ground and lower atmosphere with nowhere to go, and the temperature climbs toward its peak. The heat compounds, like an interest-bearing account where the balance grows the longer the dome holds. This compounding nature is why the duration of a blocking pattern is so critical. A system that holds for 3 days produces a hot spell. The same block holding for 8 or 10 days can create a catastrophe, because those extra days are when the compounding truly takes hold. While the dome's strength sets a ceiling for the heat, its persistence determines how close the temperature actually climbs to it. There is a grim elegance in how these effects reinforce one another. The sinking air warms the atmosphere through compression while also destroying clouds. This lets in more sun, which heats the ground. The heated ground dries out, removing the cooling effect of evaporation, which lets the ground heat even faster, which in turn heats the air above it even more. And since the dome itself is a region of powerful sinking air, it simply suppresses any attempt at cloud formation or storms that might break the spell. Every part of the system feeds every other part. With no internal break, the only thing that can stop it is an external force large enough to shove the stalled jet stream back into motion. Until that happens, the dome just runs and the temperature just climbs. This is how an 80-year-old record can be broken in the month of May, not with one freak hot afternoon, but with a high-pressure dome that locks into place day after day. It compresses the air from above to warm it, clears the sky for the sun to hammer down unobstructed, and bakes the ground until the ground itself loses the power to cool. Layer upon layer, day upon day, the heat is built. When several of those days stack together, the thermometer at a place like Heathrow finally climbs past a number that has stood since the era of the First and Second World Wars. Now, it is true that warm air drawn up from Northwest Africa and the Sahara did happen, and it added to the total heat, especially as the week went on and winds turned more southerly. It is helpful to picture it as a second burner, switched on under a pot that was already boiling. But the pot was already boiling because of the dome, the descent, the compression, the cloudless sky, and the baking of the dried-out ground. That is the primary fire. The Saharan air was the garnish on top of a dish the dome had already cooked. There is a useful way to feel the difference between the two ways heat reaches a place, and it is worth holding on to because it cuts through so much confused coverage. Imagine the difference between a fan heater and an oven. A fan heater blows hot air at you. The heat is generated in a coil and transported on a current of moving air. If you stand out of the airflow, you are fine. That is the imported heat model, the blowtorch of desert air. It does happen, but it is not usually the main event in a record-breaking heat dome. An oven works differently. It does not blow hot air at the food. It surrounds the food with a still, enclosed, heated space. The food cooks because it is sitting inside that space, with nowhere to go. A heat dome is an oven, not a fan heater. The land is not being blasted by a current of hot air from elsewhere. It is sitting inside a vast, still volume of descending, compressing, self-heating air. And it is cooking because it is inside the oven. This is why standing in the shade does not save you, and why a heat dome can be so relentless. You cannot step out of the airflow because there is no airflow to step out of. You are inside the box. This, then, is how a single nation gets cooked. A blocking high parks overhead, and the physics of descending air does the rest. But the Omega block over Europe in late May was not a small thing sitting over one country. It was a continental-scale structure. The arch of that Omega was wide enough to pull not one nation, but most of a continent under its heat. When you look at what was happening at the same time across Spain, Portugal, France, and Germany, you start to see the true size of the thing that the jet stream had built. Britain, for all the drama of its broken record, was actually on the cooler northern edge of this event. To see the full ferocity of the Omega block, you have to look south to the countries sitting more squarely under the center of that high-pressure arch, where the numbers are frankly staggering. Take a single day the Sunday before the British record fell, and look at what national weather services were recording. In Spain, the town of Montoro in Cordoba registered 38.1 degrees Celsius, which is almost 101 degrees Fahrenheit. In Portugal, at Amara, the thermometer reached 34.2 degrees. In France, a place called Prun recorded 35.9 degrees. In Germany, Regensburg in Bavaria hit 33.2 degrees. And on that same Sunday, Teddington Bushy Park in London had already reached 32.8 degrees, the exact figure of the old national record that had stood since the World Wars. Italy, on that same day, was running between 31 and 34 degrees, completing the picture of a continent under a single, immense dome of heat. It is worth pausing to consider a few of these temperature readings, as their human significance can easily be lost in a simple list. In Spain, the mercury reached 38.1 degrees Celsius. While Spain is certainly accustomed to heat, this particular reading was recorded in May, weeks before the intense furnace of its summer typically ignites. A temperature approaching 101 degrees Fahrenheit in the spring is the kind of event that places immense strain on power grids from surging air conditioner use, transforms outdoor labor into a genuinely hazardous activity, and can overwhelm hospitals with vulnerable individuals. Farther north, central France, a region of farms and ancient towns, registered 35.9 degrees, a landscape that is emphatically not a desert. Meanwhile, Bavaria, in southern Germany, a place more often associated with cool forests and snow, experienced heat near 33.2 degrees, or 92 Fahrenheit. It is crucial to remember that this was not a fleeting moment. The heat dome remained anchored for days, meaning these figures were not isolated peaks, but representative samples of a prolonged continent-wide siege of warmth. Each number stands for millions of people whose daily lives were suddenly taking place under a sky that had become something their infrastructure was never designed to withstand. If we look at the list of affected nations again, the sheer geographic scope of the event becomes clear. Spain, Portugal, France, the United Kingdom, Germany, and Italy. This was far more than a localized heat wave. It encompassed a vast portion of a hemisphere, from the Atlantic shores of the Iberian Peninsula to the heart of Central Europe, and from the Mediterranean all the way to the British Isles. An entire continent was baking under the same afternoon sun. This is the visual signature of an omega block when its arch grows wide enough to blanket a continent. At that moment, every one of those countries was situated beneath the same immense dome of sinking, compressing, and cloud-obliterating high pressure. Yet, the raw temperature figures, as startling as they are, do not fully convey the extraordinary nature of this event. To truly understand its magnitude, we must shift our focus from the absolute numbers to the deviation from the norm. The critical question is not simply how hot was it, but rather how much hotter was it than it should have been. Every location on Earth has a long-term average temperature for any given day, a climatological baseline established from decades of records. For late May, each of those European nations has an expected ordinary temperature, and none of them are anywhere near the figures that were recorded. Across the entire affected region, temperatures soared to approximately 12 to 16 degrees Celsius above the long-term average for that date. It is important to let that number resonate. This was not a minor 1 or 2 degree spike that is forgotten a week later, nor was it a 5-degree rise that might be considered a notable hot spell. This was 12 to 16 degrees above normal, which in Fahrenheit terms translates to a staggering 22 to 29 degrees hotter than it was supposed to be. An anomaly of this size is not merely a warm spell, it signifies the atmosphere operating in a completely different mode than the calendar would suggest. It was late May behaving like a severe late July. There is a fundamental reason why meteorologists focus on this anomaly, the departure from the normal, and understanding it will change how you interpret heat-related headlines forever. An absolute temperature, taken in isolation, can be deceptive. A reading of 38 degrees Celsius in a desert town during high summer is simply a hot day, unremarkable and expected. However, that same 8-degree reading in a place and season where the norm is 20 degrees represents an extraordinary event. The raw number is identical, but its meaning is profoundly different. What distinguishes ordinary weather from a truly anomalous event is not the peak temperature itself, but the distance between that temperature and its expected value. In late May of 2026, that distance across Western Europe was enormous, a gap of 12 to 16 degrees Celsius. When you view an anomaly map of an event like this, a map that colors each region based on how far its temperature deviates from the norm, the picture is striking. The affected part of Europe does not appear as a slightly warmer shade of its usual color. Instead, it is painted in a deep, angry, saturated red, a color that the map's scale typically reserves for only the most extreme departures it can depict. The map is not merely showing a warm Europe, it is showing a continent that, for a few days, seemed to have swapped its climate for that of an entirely different and much hotter part of the world. There is also a particular cruelty to heat that arrives so early in the year, a human factor that deserves recognition. The impact of heat is not just a matter of temperature, it is also a matter of acclimatization. A human body that endures a long, hot summer gradually adjusts. Physiologically, it learns to sweat more efficiently and manage the thermal load. By August, a population that has lived through June and July has developed a degree of tolerance. But a late May heatwave strikes a population fresh from winter and a mild spring. No one is acclimatized. The body has no summer conditioning to rely on. Consequently, a specific temperature in May is, in a very real physiological sense, more dangerous than the identical temperature in August, because it impacts a population that is unprepared. This is one of the quiet reasons why early season heat events, those that arrive before our bodies and societies have adjusted, often prove to be disproportionately harmful. The calendar may have said spring, but no one's body had received the message that it needed to function as if it were deep summer. as meteorologists observed an anomaly of this magnitude spreading across an entire continent. The language they used to describe it began to shift. This was no longer framed as a simple warm spell or even a conventional heat wave. Expert analysis described it as an extraordinary thermodynamic plume, a massive core of extreme warmth being driven over Spain, Portugal, Ireland, the United Kingdom, France, and Germany. Forecasters warned of a high probability that all-time station records would be shattered across multiple countries as the atmospheric ridge expanded and intensified. The word choice is significant, not break, but shatter. There is a profound difference between those terms, the same difference observed at Heathrow, where the previous record was not merely edged out, but cleared by nearly a full degree. Finally, there is one more measurement, the most technical in this story, but in some ways, the most revealing. It is the number that tells us the heat dome itself was a historic phenomenon, and it is worth understanding. When meteorologists want to assess the strength of a high-pressure system, they do not rely solely on surface temperatures. They examine something called geopotential height, specifically at the 500 millibar level. This corresponds to an altitude of roughly 3 miles, where the air pressure has fallen to 500 millibars. In a powerful high-pressure ridge, this layer of the atmosphere is physically pushed upward, offering a direct measure of the system's immense strength. The entire dome of air bulges upward, and the height of the 500 millibar level provides a direct measurement of just how powerful, tall, and dominant that high-pressure system truly is. During this event, ensemble guidance from forecast models indicated that these 500 millibar heights over Europe could approach all-time record levels for the month of May. It is a detail worth pausing on. The issue was not merely that the surface was experiencing record heat. The dome itself, the very structure in the sky responsible for the warming, was among the most potent ever analyzed over Europe for that time of year. In this way, the cause was as extreme as the effect. The atmosphere had not just produced a record-shattering outcome, it had constructed a record-shattering machine to achieve it. To truly appreciate the physics at play, the concept of geopotential height is essential, as it distinguishes a casual observation of the event from a genuine understanding. Most coverage of a heat wave presents a surface temperature map, with countries painted in shades of red and orange. That map, however, only illustrates the symptom. The geopotential height map, the one that depicts the shape and intensity of the pressure pattern 3 miles above the ground, reveals the cause. And when forecasters studied that upper air map for late May 2026, they saw a high-pressure ridge bulging to heights rarely witnessed over Europe during May in the entire history of modern measurement. The dome was not simply strong. According to the data, it was approaching a level of historic power for that specific calendar date. Now, we can connect this back to the principles we have established. A dome of near-record strength implies a cascade of related effects: near-record descent of air, near-record compression, and a near-record efficient engine for manufacturing heat, all sitting stationary over the continent. Seen through this lens, the shattered surface temperature records were not a surprise. They were the predictable output of an atmospheric machine that was itself operating at a near-record setting. The cause perfectly matched the effect. This is the fundamental coherence of the event, and it explains why meteorologists observing it were not confused. They were certainly alarmed, but the physics were clear. The sky was behaving exactly as a near-record dome should. With this, the European half of the picture comes into full focus. An amplified jet stream had buckled into a massive, stalled omega pattern. Locked beneath its central arch was a high-pressure ridge of almost unprecedented strength. Under this ridge, a continent of nations baked together in temperatures soaring 12 to 16 degrees Celsius above normal, shattering all-time station records. This phenomenon stands as a complete, coherent, and singular event, more than enough to be the subject of its own story. Yet, it represents only half of what was unfolding across the Northern Hemisphere. That is because the same contorted, stalled jet stream, the very river of wind that drew the Omega over Europe, does not simply stop at the continent's edge. It wraps around the entire planet, and the way it loops, dips, and ridges as it continues eastward determines the weather over Asia just as surely as it dictated the conditions over Spain. To see why this is a global story, not just a European one, we must follow the jet stream onward and examine what the rest of that wave pattern was doing. A jet stream this amplified does not merely create one zone of extreme heat. It divides an entire hemisphere into sharp, violent contrasts. The other half of the wave is as much a part of the narrative as the heat itself. This brings us to a statement that sounds like a contradiction, but is not. The very same jet stream pattern that was generating record heat over Western Europe was, during the same days, producing unseasonably cold, grey, and showery weather in other parts of the hemisphere. These two phenomena, the extreme heat and the unseasonable chill, were not separate weather stories that happened to occur at the same time. They were, in fact, the same story. They were two faces of a single wave. Think back to the shape of the jet stream, that winding river of air seen from above. Recall that where the river loops northward, it allows warm air to bulge up from the south, and where it loops southward, it drags cold air down from the north. An amplified jet stream, one with enormous waves, intensifies both of these actions. The northward loops travel farther north, pulling warmth deeper into regions that should be cool. At the same time, the southward loops plunge farther south, pulling cold air deeper into regions that should be warm. The bigger the wave, the sharper the contrast between its crest and its trough becomes. So, when the jet stream amplified into that great omega pattern over Europe, the arch of the omega delivered the intense heat. But an omega block has 2 feet. On either side of that central, heat-producing ridge, the jet stream plunged southward, forming deep troughs of low pressure. The land underneath those troughs experienced the opposite of a heat dome. It received cool air pulled down from the north, low pressure, clouds, showers, and a raw, grey, unspring-like chill. This effect was visible even within Europe itself. Forecasters noted that the heat across the central part of the continent was expected to ease temporarily midweek as a weak cold front pushed down from the north. This cold front was not an unrelated event. It was the edge of one of the troughs, the cool foot of the omega nudging its way onto the continent. If you were to pull the camera back far enough to see the entire Northern Hemisphere at once, you would have witnessed this pattern repeated all the way around the globe. A band of extreme heat here, situated under a ridge. A band of unseasonable cool there, situated under a trough. Another ridge, another zone of heat, another trough, another zone of cool. The whole hemisphere was carved into alternating stripes of hot and cold, like the segments of an orange, with each stripe sitting beneath its corresponding piece of the great, waving jet stream. In the same window of time that Europe was shattering heat records, other parts of the world, including areas of North America, were sitting under a cooler, more unsettled, and showery regime. It was the same wave, just a different segment, producing the opposite weather. It is worth pausing to consider how counterintuitive this is, because it cuts against a deep-seated instinct. When we hear that one part of the world is unusually hot, while another is unusually cold, our minds tend to treat these as two separate, even contradictory, pieces of information. The heat seems to argue for one conclusion, the cold for the opposite, and we instinctively want to file them in different mental drawers. But the atmosphere does not operate in separate drawers. In this case, the heat and the cold were not arguing with each other. They were collaborating, two inseparable parts of a single, unified atmospheric dance. They were two sides of the same coin, a peak and a valley born from a single atmospheric wave. Just as a ripple on water cannot have a high point without a low one, these weather patterns were inextricably linked. The very mechanism that amplified the wave's crest, baking Europe under intense heat, simultaneously deepened its adjacent troughs, casting a profound chill over the regions below. This presents a crucial insight into our planet's climate. A simultaneous occurrence of record warmth in one area and unseasonable cold in another is not a sign of atmospheric confusion. On the contrary, it is one of the clearest possible signatures of a powerfully amplified jet stream. The stark contrast is itself the fingerprint, pointing to a more profound way of interpreting global weather reports. In any given week, one can easily find headlines of heat waves somewhere and cold snaps elsewhere. It is tempting to view these as cancelling each other out, as if the planet's weather were merely a chaotic and random system where extremes eventually balance. But when the heat and the cold are this sharp, and when they are arranged in a distinct, alternating pattern across the hemisphere, they are not cancelling out, they are communicating. They are spelling out the precise shape of the jet stream. A hemisphere marked by locked bands of intense heat and cold is not a world of random noise. It is a world whose weather has been captured and organized, held in the grip of an amplified, stationary wave. When read correctly, the noise becomes a clear and powerful signal. This is why a meteorologist observing a map of the Northern Hemisphere during this event would have seen not chaos, but an almost unsettling order. They would have recognized a clean, repeating wave-like pattern, stamped across the entire hemisphere, with the zones of heat and cold laid out in methodical bands. Each band corresponded perfectly to a crest or a trough in the jet stream. The sharper and more locked in these bands appeared, the more amplified the wave. And in late May of 2026, the bands were exceptionally sharp, and they were locked in place. This is the deepest reason why this event was a single global story, not a collection of separate local incidents. It wasn't just that several places were hot simultaneously, in the way unrelated events can coincide by chance. It was that the heat in Europe, the heat elsewhere, and the cool in between were all manifestations of a single hemisphere-spanning structure. One jet stream, one wave pattern, one atmospheric configuration stretched across the top of the world, deciding all at once which nations would burn and which would shiver. And once this interconnectedness is understood, it becomes clear why our journey must continue. There is a third major region of the Northern Hemisphere that was caught in those very same days under its own brutal wave of heat. This is a region inhabited by more than 1 billion people, and they were not enjoying a record-breaking holiday weekend. They were enduring something far more perilous, a situation that was already claiming lives. To see the true scale of what this contorted jet stream had wrought, we have to leave Europe behind entirely. We must travel several thousand miles to the southeast, to the vast, sun-scorched plains of northern India. Part 6. The Plains of India Under the Same Sky. While Western Europe was experiencing a record-breaking but, for most, survivable heat wave, the Indian subcontinent was enduring heat of a completely different magnitude. This is the part of the story where the numbers cease to be merely remarkable and become truly frightening. In the town of Banda, located in the northern Indian state of Uttar Pradesh, the temperature soared to 48.2 degrees Celsius. It is worth taking a moment to convert that figure, as it deserves the full weight of its other unit. 48.2 degrees Celsius is just under 119 degrees Fahrenheit. This was the hottest location in the entire country, running approximately 4.5 degrees Celsius above what is normal for Banda, even during its hottest season. In the Vidarbha region of Maharashtra state, the town of Brahmapuri recorded 47.2 degrees Celsius, or around 117 degrees Fahrenheit. Meanwhile, the capital city of Delhi, home to tens of millions, was forecast to reach 44 to 45 degrees Celsius, comfortably over 111 degrees Fahrenheit, day after day, under repeated official heat alerts. To grasp the reality of these conditions, it helps to understand what a temperature like 48 degrees Celsius actually does to a human being, because the number itself can easily slide by as just another statistic. The human body maintains an internal temperature of around 37 degrees Celsius. When the surrounding air is hot, it has exactly one primary tool for shedding excess heat: sweat. The body pushes moisture to the skin, which then evaporates, carrying heat away with it. This is the same principle of evaporative cooling we see in damp soil, but this vital mechanism has brutal limits. When the air temperature climbs to 48 degrees Celsius, the environment is 11 degrees hotter than the body's own core. At this point, the body is no longer simply trying to stay cool. It is fighting an environment that is actively pouring heat into it from all directions. Sweating can still work for a time, but it comes at the cost of enormous amounts of water. If that water is not replenished, the body dehydrates, the sweating process falters, and the core temperature begins to climb. The human body has an incredibly narrow tolerance for this. A rise of just a few degrees in internal temperature is the difference between discomfort and catastrophic organ failure. This is the ground-level meaning of a number like 48.2 degrees. It signifies an environment where the body's only cooling tool is being overwhelmed, and where survival becomes entirely dependent on shade, on water, and on rest. These are three things that are not equally available to everyone, and this final point is the most critical for understanding why the same degree of heat can be so much deadlier in some places than in others. Heat does not affect a population uniformly. It seeks out the vulnerabilities. It finds the person who must work outdoors because their livelihood offers no alternative: the construction worker, the farmer, the street vendor. It finds the person with no cool room for retreat, no air conditioning, and sometimes no reliable electricity. It finds the very old and the very young, whose bodies are less effective at regulating temperature. It finds the person who is already ill. In this sense, a heat wave acts as a kind of stress test applied to an entire society at once, and it ruthlessly exposes every inequality in that society's access to shade, water, rest, and cooling. The plains of northern India in late May are home to vast numbers of people for whom these protections are either thin or entirely absent. This is precisely why a heat wave there is not what it largely was in Britain, a record-breaking but survivable weekend. In India, it becomes a siege, and a siege with casualties. In India, a nation accustomed to intense heat, the situation had reached a critical point. The country's National Weather Service, the India Meteorological Department, had broadcast extensive heatwave warnings across a vast swath of the subcontinent. The alerts covered states from Delhi and Rajasthan to Punjab, Haryana, and Uttar Pradesh, extending through Madhya Pradesh, Vidarbha, Chhattisgarh, Bihar, and Telangana. This was not a localized event affecting a single region. It was a significant portion of one of the most densely populated countries on Earth, all simultaneously under an official danger advisory. The message was clear. The heat was perilous and was projected to continue its grip through the end of the month. This brings us to a crucial concept, one that helps explain why heat is such an insidious threat. It has been called a silent killer, and that silence is the very source of its danger. A hurricane or a flood makes its presence known with overwhelming force. A tornado is a visible, violent spectacle, leaving behind a trail of wreckage that is easily photographed and tells a clear story of devastation. Heat, however, operates differently. It claims its victims quietly, often indoors, targeting the elderly, the isolated, and those already in frail health. It leaves no flattened buildings or dramatic footage. Its casualties are not concentrated in a single, observable catastrophe but are spread out, one by one, across an entire region. Often, the official cause of death will not even mention the heat that tipped the scales. This silent nature means the danger is consistently underestimated, both by the public and by the very systems designed to measure its impact. A society will brace for an approaching hurricane, yet it may not react with the same urgency to a heat wave, even when a severe season of heat can ultimately prove to be the more lethal of the two. In India, this was not an abstract concern or a distant curiosity, as it might have been in cooler climates like London. The heat was having real, fatal consequences. Officials in the southern state of Telangana confirmed that 16 individuals had succumbed to heat stroke across 7 different districts. In the city of Indore, located in Madhya Pradesh, a 4-year-old girl tragically died from suspected suffocation after being trapped inside a car during the intense afternoon heat. These are not mere statistics. They represent the human reality of what a number like 48.2 degrees Celsius truly signifies. It is a temperature that becomes a physical siege in a place where hundreds of millions of people must work outdoors, where a cool room is not a guaranteed refuge, and where the heat is not a topic for casual conversation but an oppressive, life-threatening force. It is at this point that we must proceed with great care and honesty, as stories of this nature can become fertile ground for misinformation, something calm space is committed to avoiding. As the heat wave intensified, a claim began to spread online, asserting that nearly 50,000 people had died. You may have encountered this staggering figure, and it is vital to address it directly. The truth is more important than a more sensational number. This claim of nearly 50,000 deaths is not substantiated by any official reporting. The verified, confirmed death tolls from this specific event were vastly lower, 16 confirmed in Telangana, with other individual tragedies reported elsewhere. A precise, dramatic 5-figure number presented as an established fact without official backing is a viral claim, not a verified statistic, and should be treated with skepticism. However, it is equally important not to swing to the opposite extreme and assume that heat is harmless. The careful, honest position acknowledges that heat is a serious and chronic killer. One of the most troubling realities of heat mortality globally is that it is almost certainly undercounted, often significantly so. When a vulnerable person with a heart condition dies during a heat wave, the death certificate might list heart failure as the cause, with the contributing role of the extreme heat never appearing in the official tally. The truth, therefore, is a nuanced one. The viral 50,000 figure is not credible and should not be repeated. At the same time, the true human cost of severe heat across a nation the size of India is grave and very likely far exceeds what the confirmed counts will ever reveal. Honesty requires us to hold both of these truths at once. This leads to the most important question for our narrative. Was the heat wave in India the same event as the one in Europe? The careful answer is no, they were not the same event, but they were the same kind of phenomenon, connected by the same hemispheric pattern. Late May in India is always hot. The pre-monsoon season across the northern Indian plains consistently produces some of the most brutal heat on the planet year after year. So, the existence of a heat wave in India during May is not, in itself, surprising. What links it to our broader story is that during those same days, India was the third major landmass in the Northern Hemisphere, positioned directly under the hot side of that same amplified, contorted jet stream wave. One ridge of high pressure sat over Europe, and another sat over India. The atmospheric pattern that had divided the hemisphere into bands of hot and cool air had placed 2 of its most intense heat zones over 2 of the world's most populated regions in the very same week. This is precisely why a global perspective is so essential. When you pull the camera back to view the entire Northern Hemisphere, You do not see a European story with an unrelated Indian footnote. Instead, you see a single planet-scale wave. You see that the geography of human settlement has placed enormous numbers of people directly beneath its hottest segments. That is the connecting thread. That is what ties Baikonur to Heathrow. It is not that the same mass of air touched both locations, because it did not. The connection is that the same overarching atmospheric configuration, the same undulating river of wind, left its fingerprints on both places simultaneously. It is worth being precise about this connection between the Indian and European heat, because this is exactly the kind of topic where a loose statement can become misinformation, while a careful one leads to genuine understanding. I am not suggesting that the same body of hot air travelled from London to Baikonur. The air over Britain and the air over the Indian plains are separated by thousands of miles and governed by entirely different regional weather systems. Nor am I claiming that Europe's omega block directly caused India's heatwave. The actual claim is more subtle and, in many ways, more profound. It is that the jet stream is a single, continuous, hemisphere-encircling river of wind. When that river enters a state of strong amplification, forming large, dramatic waves, it does so all the way around the globe. It does not become amplified over Europe while remaining calm everywhere else. The entire system shifts, creating interconnected consequences in distant parts of the world. The waviness of the jet stream is a property of the entire system. By its very nature, a strongly undulating jet stream produces a series of corresponding ridges and troughs, spaced out across the whole of the Northern Hemisphere. In this instance, Europe happened to be situated directly beneath one of those high-pressure ridges. During those same days, the northern region of India found itself within a zone of intense heat, a position consistent with the hot side of that very same global wave pattern. The critical insight here is that the connection is not a shared mass of air traveling between the two continents. Instead, the link is a shared origin, a single, amplified atmospheric configuration manifesting its effects in multiple locations at once. This distinction is precisely why this story must be understood on a global scale, rather than as a European event with a secondary note about Asia. If the heat in Europe and the heat in India were merely two unrelated, coincidental spells of hot weather, then connecting them would be a narrative trick, designed to make a local story feel more significant than it was. But these events are not unrelated. They are two distinct symptoms of a single underlying condition. Once you begin to see the atmosphere in this way, it changes your perspective entirely. You start to view a map of the entire Northern Hemisphere, not by asking where it is hot, but by asking what shape the jet stream is in. The shape of that river of air is what ultimately determines where the heat will build. The heat is the symptom, the wave is the cause. And in late May of 2026, that cause held both Europe and India in its grip. There is, however, one more element to the Indian side of this story, a piece that offers both a glimmer of hope and a stark warning about how suddenly such extreme heat can be broken. India's heat wave had a potential end date built into its very fabric. Forecasters anticipated the arrival of the southwest monsoon, the great annual deluge of rain that shatters the pre-monsoon heat across the subcontinent. It was expected around the 26th of May, slightly ahead of its typical schedule. When the monsoon arrives, the heat does not simply fade away. It is often broken abruptly as the rains sweep across the land. This means that India's deadly heat may well have been cut short just days after its peak by the early arrival of these rains. But notice what this reveals. The relief, when it finally comes, arrives because the entire atmospheric pattern has changed. The heat only ends when the configuration that produced it at last begins to shift. The monsoon itself is a vast seasonal reorganization of the whole circulatory system. This observation points us directly back to the true subject of this entire narrative. Everywhere we look, in Europe and in India, the presence of extreme heat is governed by a pattern. and the heat only dissipates when that pattern moves on. This brings us to the question we have been circling from the start. If this distorted jet stream pattern is what determines whether 1 billion people are subjected to life-threatening heat, then we must understand why the pattern became so extreme this time, and it compels us to ask if something is loading the dice in favor of such events. As it turns out, there is, and the science that measures this influence has put a number on it. Up to this point, our exploration has been almost entirely focused on the mechanics of the atmosphere, the jet stream, the omega block, the high-pressure ridge, and the physics of sinking, compressing air. This was a deliberate choice, because these mechanisms represent the honest, physical core of the story. The intense heat over Britain, Spain, and India was directly produced by a blocking pattern, and a blocking pattern is, fundamentally, a weather event. It is the atmosphere doing one of the things the atmosphere has always done. Omega blocks are not a new phenomenon. Heat waves are not new. The jet stream has been waving and occasionally stalling for as long as it has existed. A fair and skeptical observer, having followed this explanation, might reasonably conclude, you have described the mechanism, and the mechanism is natural. So what is the problem? It was a hot spell caused by a high-pressure system. These things simply happen. This is a valid challenge, and it deserves a precise scientific answer, not a slogan. And the precise answer is this: the mechanism is indeed natural. The block is a feature of weather. But the sheer severity of what that natural mechanism produced, the fact that an 80-year record was not merely broken, but completely surpassed by most of a degree that part of the story is not fully explained by the machinery of the atmosphere alone, and a specific branch of science has been developed to measure that very gap. This field is known as climate attribution science, and its approach is genuinely clever. It avoids asking a vague, unanswerable question like, did climate change cause this heat wave? A serious scientist will not engage with such a poorly formed query. Instead, attribution science poses a much sharper and therefore answerable question. Given that this specific weather pattern occurred, how much did the warmer background climate alter the probability of it producing a result this extreme? It is worth taking a moment to understand, at least in outline, how that question is answered, because the method is elegant and provides a powerful defense against flawed arguments. Attribution scientists do something that sounds like it belongs in science fiction, but is in fact a standard tool in modern climatology. They construct two distinct versions of our planet inside their supercomputers. The first version is a model of the real Earth, the world as it is today, with all the warming that human greenhouse gas emissions have already caused baked into the system. The second version is a counterfactual Earth. This is a simulated world that is identical to our own in every way but one, a world in which those extra greenhouse gases were never added to the atmosphere. It is a world running on the cooler, pre-industrial climate. They then run the weather over and over again in each of these two worlds, simulating hundreds or even thousands of years in both the real-world climate model and the counterfactual one. After all these simulations are complete, they simply count. In how many of the simulated years in the real, warmer world did an extreme event as severe as this one happen? And in how many of the simulated years in the cooler, counterfactual world did that same extreme occur? The ratio between those two numbers is the answer. It is the factor by which the background warming has changed the odds. There is no guesswork involved. It is a careful, repeatable, statistical comparison between two modeled worlds. For the British heatwave, scientists working with the Met Office conducted this exact analysis, and they arrived at a specific, quotable finding. They determined that the probability of breaking the old May record, that is, exceeding 32.8 degrees Celsius, is now roughly 3 times more likely in our climate today than it would have been in a natural climate, one without the warming caused by greenhouse gas emissions. 3 times more likely. That is the verified scientific basis for a figure. You may have seen in public discussions the claim that this kind of heat is 300% more likely, or 3 times as likely, is grounded in this rigorous work. In contrast to speculative figures, a formal attribution study provides a grounded, verifiable analysis. The researchers behind it also offered a more vivid way to understand the data by translating it into return periods. What their work revealed is a profound shift in probability. An event that, in a cooler climate, might have occurred just once in 100 years, has now become an event expected roughly once every 33 years. Let's pause to consider what this truly means. In the past, a May this hot would have been a once-in-a-century anomaly, something a person might experience a single time in their life, if at all. In our present-day climate, however, that same level of extreme heat is now something a nation can anticipate, about 3 times per century. It has transformed from an extraordinary, once-in-a-lifetime occurrence into something that could happen multiple times within a single person's lifespan. The extreme wasn't made unavoidable. It was simply made 3 times more frequent. The dice were not replaced, but they were certainly weighted. This concept of weighting is crucial, as it perfectly captures the intricate relationship between weather and the planet's overall warming. Getting this relationship right is the entire purpose of this exploration. It is essential not to conclude that climate change directly created the omega block, steered the jet stream into that specific configuration, or aimed a heat dome at London. That is not what the science indicates. The omega block itself was a weather event, a product of natural variability. It could have formed in a cooler world, and it would have still brought a period of hot weather. The critical difference lies in the starting point. In a cooler world, that same atmospheric block would have begun its work from a lower baseline temperature. Every parcel of air it compressed, and every patch of ground it baked, would have started a degree or so cooler. Consequently, the same natural pattern would have produced a hot spell, but one that fell short of the old record. Now, transport that identical pattern into our warmer baseline climate. The very same atmospheric machinery, performing the very same actions, now pushes the temperature that extra distance, crossing an 80-year threshold into record-breaking territory. The pattern is natural. The baseline upon which it operates is not. The records fall in the gap between the two. This is the very essence of what climate attribution means by amplification, rather than direct causation. A helpful way to visualize this is to think of a tide and a wave. The wave is the weather, the omega block, rolling in as it always has, sometimes large, sometimes small. The tide is the slow, steady rise of the background climate. The tide does not create the waves, but when the tide is high, every single wave reaches further up the beach than an identical wave would have at low tide. The one wave that finally surges past the high water mark and floods the promenade does so not because it was a supernatural wave, but because it arrived on top of a tide that had already risen. The omega block of late May 2026 was a wave. It broke an 80-year record because it arrived on a tide of planetary warming that has been rising for a century. This tide metaphor holds a second, deeper implication, one that transforms this from a story about a single weekend into a story about the years to come. A rising tide does not just lift the one wave that finally floods the promenade, it lifts every wave. It fundamentally alters the entire baseline against which all waves are measured. In this way, the effect of a warmed climate isn't truly about any single record-breaking event. It is about the quiet, relentless shifting of the whole distribution of weather. Hot days that were once rare become merely uncommon. Hot days that used to be uncommon become ordinary. The truly extreme, the record-shattering, the once-in-a-century event slides forward to become a once-in-a-generation phenomenon. For this to happen, nothing about the fundamental machinery of weather needs to change. The jet stream can continue its timeless dance, drawing its omegas and its ridges at the same rate it always has. But because every one of those patterns now operates on a higher baseline, the output of the entire system is shifted upward. The attribution number for this one British record, making it roughly 3 times more likely, is just a single snapshot of that larger, slower process. It is one measurement of a tide that is still coming in. This reframing is vital because it helps dissolve a false argument you will hear constantly whenever extreme heat is in the news. One side may claim, "This proves climate change," while the other retorts, "No, it was just a high-pressure system, a natural pattern, nothing to see here." The quietly frustrating truth is that both of these statements are incomplete. The real picture contains both of them at once. It was a natural high-pressure system, and the background warming made that natural system roughly 3 times more likely to break the record. These are not competing explanations fighting for the same job. They are 2 different layers of the same event. The mechanism tells you how the heat was made. The attribution tells you why the heat was a record. You need both to understand what happened, and anyone selling you only one is selling you half the story. If you take only one idea away from this, let it be this one, as it will serve you for the rest of your life every time a heat wave is in the news. There are 2 distinct questions you can ask about any extreme weather event, and almost all public confusion comes from mixing them up. The first question is, how did this happen? By what mechanism? The second question is, why was this version of it so severe? For the heat of late May 2026, the answer to the first question is the omega block, the stalled jet stream, and the descending air, all the natural machinery we have explored. That machinery is weather. The answer to the second question, why a record that had stood since the World Wars was not just broken, but cleared by most of a degree, is the warmed baseline, the risen tide, the roughly 3-fold loading of the dice. 2 questions, 2 answers, both true at once. The person who tells you it was just a high-pressure system is answering only the first question and pretending the second does not exist. The person who tells you it was simply climate change is collapsing the second answer into the first, skipping the mechanism entirely. The complete, honest, and scientifically accurate picture needs both, held together at the same time: mechanism and amplification, the how and the why it was so bad. Keep those 2 questions separate in your mind, and most of the noise around climate and weather simply resolves itself. At this point, the anatomy of the event seems clear. We can trace the distorted, stalled shape of the jet stream. We can identify the structure of the omega block, with its high-pressure ridge reaching near-record intensity. We understand the engine driving the heat, the vast column of air, sinking, compressing, and incinerating clouds as it descends. We have seen its hemispheric reach, placing 3 populated regions under the scorching bands of a single atmospheric wave. And crucially, we have a measure of the underlying influence, a warming baseline climate that made such a record-breaking event roughly 3 times more probable. This provides a complete explanation of the mechanics. But explaining the mechanism is not the same as grasping its full implications. A more unsettling question remains, one that careful scientists continue to debate. While patterns like this omega block have always been a possibility in Earth's atmosphere, are they now beginning to occur more often? Is the very river of wind that orchestrated this entire event, the jet stream itself, starting to behave in new and unpredictable ways? Everything discussed up to this point rests on what is, by the standards of atmospheric science, solid ground. The mechanics of a heat dome, the architecture of an omega block, and the attribution science finding that the British record was made about 3 times more likely by our warmer climate. These are all well-established principles. But now, we must deliberately step onto less certain terrain, because there is a fundamental question over which working scientists genuinely disagree. Intellectual honesty requires us to explore this debate, rather than presenting a simplified or premature conclusion. The question is this: the entire event we witnessed was contingent on the jet stream becoming dramatically amplified and then stalling, which locked the omega block in place for days on end. So, is this specific type of behavior, the formation of large, meandering waves that stall and create blocks, becoming more frequent as the planet continues to warm? In short, are the fundamental habits of the jet stream changing? One prominent and intuitively compelling line of reasoning argues that the answer is yes. The argument unfolds in a logical sequence. It begins with the basic principle that the jet stream is powered by the difference in temperature between the frigid pole and the warm tropics. This contrast is its engine. The critical observation that follows is that the Arctic is not warming at the same pace as the rest of the globe. It is heating up substantially faster, a phenomenon known as Arctic amplification. If the Arctic warms more rapidly than the tropics, it logically follows that the temperature difference between the pole and the equator must be shrinking. The cold end of the atmospheric engine is becoming less cold. The argument continues that if you weaken this fundamental temperature contrast, you also weaken the force that keeps the jet stream focused and strong. A powerful contrast helps maintain a taut, fast, and relatively straight jet stream, much like a rope pulled tight. But as that contrast diminishes, the theory suggests the jet stream becomes slacker, slower, and more susceptible to forming large, looping meanders. These are precisely the kinds of waves that can grow, stall, and lead to more blocking events, more omega blocks, and more stagnant weather patterns, like heat domes that lock into place and refuse to dissipate. It is a clean and elegant narrative, one that has become genuinely influential, and it is supported by the work of a number of respected scientists. However, and this is the part that intellectual honesty compels us to include, the theory is not yet settled science. Other researchers, looking at the very same atmosphere, find that the signal is either weaker than proposed, more convoluted, or simply too difficult to distinguish from the planet's ordinary, natural variability. The jet stream is a fantastically complex phenomenon, pushed and pulled by a multitude of forces. Attempting to isolate one single, clean trend against a backdrop of immense year-to-year noise is an exceptionally challenging task. Therefore, the most careful and accurate statement one can make is this: the idea that a warming Arctic is causing the jet stream to become wavier and blocking patterns more common is a serious, plausible, and actively researched hypothesis. It is not, however, a proven fact. It is best to hold this as a critical and open question, not a final conclusion. If anyone presents this issue as simple or definitively decided one way or the other, they are moving ahead of where the science currently stands. It is useful to be honest about why this particular question is so difficult to resolve, because the challenge itself is instructive. The jet stream is not a simple system with a single input and a single output. Its behavior is shaped, of course, by the temperature contrast between the pole and the equator at the surface, but it is also influenced by the temperature differences much higher in the atmosphere, which can behave quite differently. Its path is physically warped by the great mountain ranges of the hemisphere. It is molded by the patterns of warm and cold water circulating in the oceans below. It is also steered by events unfolding in the tropics, by the slow oceanic cycles of the Pacific, and even by phenomena occurring in the stratosphere, far above the weather we experience. It is, in short, a system where countless factors are all vying for control at once. On top of all this complexity, the jet stream is inherently and wildly variable from week to week and year to year, simply due to the natural chaos of the climate system. A scientist trying to detect a slow, decades-long change in its behavior is therefore searching for a faint, gradual signal buried within a roaring background of natural noise. This task is genuinely and legitimately hard, not because the scientists lack skill, but because the problem itself is profoundly complex. This is precisely why you see honest disagreement in the published research. That disagreement is not a sign of failure. It is what the frontier of a difficult science truly looks like. Within this complex field of study, there are other threads of research worth noting because they add more sharpness to the picture. For instance, some scientists have moved beyond looking only at a single wavy jet stream. They have instead studied specific configurations where the jet stream effectively splits into two parallel branches flowing over Eurasia, a phenomenon sometimes referred to as persistent double jet states. Their findings suggest that these particular configurations are strongly linked to the formation of stubborn, heat-producing ridges that park themselves over Europe, exactly the kind of pattern observed in the recent event. Further research has even connected the acceleration of heatwave trends in Western Europe specifically to an increase in these persistent double jet states. This represents a more targeted finding than the broader Arctic argument, and it points in a similarly worrying direction. And this leads us to what is perhaps the most sobering thread of all in this unfolding scientific story. There is a compelling reason why these questions are so critical in Western Europe. In recent decades, the region has become a focal point for extreme heat, developing in a way that has taken many researchers by surprise. The continent has been struck by a succession of intense heat events, which, when viewed together, suggest less a run of bad fortune and more a coherent trend. By several metrics, the heat there has intensified at a rate that standard climate projections had not prepared anyone for. This discrepancy is a specific, documented puzzle within the scientific community, and the primary suspect behind this puzzle is, once again, atmospheric circulation, the behavior of the jet stream, and the patterns it tends to favor. If, for any number of reasons, the jet stream over Eurasia is becoming more susceptible to the stalled, ridge-building formations that trap heat over Europe, then the continent would naturally warm faster than a simulation that fails to capture this tendency. This appears to be exactly what has been happening. Published research indicates that heat extremes in Western Europe have indeed been accelerating more rapidly than climate models predicted. The suspected cause is precisely this type of circulatory behavior, the changing patterns of the jet stream, which the models do not yet fully represent. Consider for a moment what this implies if it proves to be true. Our projections for Europe's future heat are constructed largely from these same climate models. If the real atmosphere is generating heat extremes faster than the models suggest it should, because of jet stream dynamics the models underestimate, then our forecasts for the future may be far too conservative. The actual risk could be outpacing the official projections. This is not a comforting realization, and it would be disingenuous to pretend otherwise. It is important to be precise about the scientific standing of these ideas. This is the speculative frontier of climate science. The physical mechanism of the heat dome is a certainty. The attribution science, which quantifies the role of climate change, is also solid. However, the theory that the jet stream itself is undergoing a fundamental shift in its behavior remains genuinely uncertain. I have been careful to flag this uncertainty at each step, because that is the scientific truth. But uncertainty does not imply insignificance. It is an uncertainty akin to hearing an unfamiliar sound from your car's engine. You may not know its exact cause, but that is precisely why it warrants careful investigation rather than dismissal. The possibility that the very machinery of our hemisphere's weather is altering its fundamental operations is not a cause for alarmism, but it absolutely demands our focused, clear-eyed attention. This brings us, finally, to the questions this entire event leaves us to confront, including those that the internet predictably answered in the least helpful ways. Whenever a weather event of this magnitude unfolds, when records are shattered, maps glow dark red, and the story captures global attention, a secondary weather system begins to form. This one, however, does not exist in the atmosphere, but online. It is worthwhile to navigate through what this second system generated, because distinguishing the real signal from the surrounding noise is essential to understanding what truly occurred. The most prevalent alternative explanation, one that emerges after nearly every extreme heat event, is the claim that the heat was deliberately manufactured. The theory posits that some facility, a weather modification program, or a geoengineering project intentionally reached into the atmosphere and constructed the heat dome. I want to engage with this idea seriously, not with dismissiveness, because the most honest response is not mockery. It is simple arithmetic. Reflect on the immense scale of what we have been discussing. An omega block stretching across an entire continent, a high-pressure ridge with near-record geopotential heights, and a wave in the jet stream measuring 1,000 miles or more from one crest to the next. This is a structure with a quantifiable energy locked inside it that is, quite literally, planetary in scale. Now, compare that to the actual tools that humanity has at its disposal. The various facilities named in these theories operate at power levels that are, by comparison, almost unimaginably small. The chasm between the energy of a continental jet stream pattern and the energy output of any installation ever built by humankind is not a gap that can be bridged with a clever technique. It is a gap of many, many orders of magnitude. It represents the difference between a person holding a garden hose and the entirety of the Atlantic Ocean. Let's take cloud seeding, the one genuinely existing form of weather modification. What are its true capabilities? On a favorable day, and under ideal conditions, it can gently encourage a pre-existing cloud to release slightly more of the rain it was already poised to deliver. That is the honest upper limit of the technology. It cannot summon a continent-spanning ridge of high pressure from thin air. It cannot reach 30,000 feet into the sky and force the jet stream into an omega configuration. And it certainly cannot hold that shape in place for a week against the immense power of the entire atmosphere. The claimed cause and the observed effect do not exist in the same universe of scale. This mismatch is not an evasion, it is the answer. Here on Calm Space, our approach is to address these claims directly, weigh them seriously, and then measure them against the laws of physics. When measured against physics, the engineered heat dome explanation simply cannot survive contact with its own energy budget. Then we have the opposite claim, which arrives from the other direction. This argument states that the event was nothing more than ordinary weather. Heat waves have always existed, it says, and May has always had its warm spells. The media, in this view, is simply hyping a routine hot weekend. The proper response to this is also not mockery, because the first part of the statement is undeniably true. Heat waves have always happened, and warm periods in May are nothing new. But when you examine the specific details of this event, the dismissal falls apart. An 80-year-old national record was not just tied, it was shattered, and by most of a full degree. The temperature anomalies across Europe were not within the normal range. They were 12 to 16 degrees Celsius above average, and the attribution science assigned a hard number to it, finding the event was roughly 3 times more likely to occur in our current climate. The statement heat waves happen is true. The conclusion, therefore, this particular heat wave is statistically unremarkable, does not follow, and it is the data itself that prevents that leap in logic. It is worth pausing for a moment to consider why the idea of engineered heat is so persistently compelling. Understanding its appeal is more productive than simply swatting the claim aside. A heat dome, in a strange sense, makes for an unsatisfying villain. It is an invisible force, an abstract entity with no face. When a vast and frightening event unfolds, it is a deeply human response to search for agency, for a reason behind it. We look for a hand on the lever, for some form of intention. This is because the human mind, faced with something so large and harmful, craves a story with a villain. The concept of a deliberately engineered heatwave, as terrifying as it sounds, offers a strange sort of comfort. It suggests that if someone started this, then someone could also stop it. It implies that our world is governed by intention, not by the cold, indifferent laws of physics. One can understand the appeal of such a narrative. Yet, the honest answer lies not in a conspiracy, but in arithmetic. The atmosphere is not being guided by a hidden hand, because no such entity possesses the power required to steer it. The discomfort of a story without a villain is a genuine feeling, but it is not a valid reason to invent one. Alongside this idea, several other claims circulated within the same online discourse, and they each merit a clear and honest examination. One popular theory suggested that the temperature records themselves were fraudulent, perhaps inflated by poorly positioned thermometers or the effects of urban heat. The truthful answer here acknowledges a real phenomenon embedded within a false conclusion. The placement of scientific instruments is indeed a serious concern for researchers, which is precisely why national weather services dedicate resources to studying it, correcting for it, and transparently publishing their methodologies. The fact that the British temperature record was initially announced as provisional, pending verification, is a testament to this scientific scrutiny, not a sign of deception. While urban warming is a real effect, it cannot explain a synchronized signal appearing across countless separate stations in numerous countries all at once. Another claim pointed to the sun, suggesting that solar activity was the true driver of the heat. However, solar output during this period was not unusually high. More fundamentally, the formation of a heat dome is not a matter of sunlight intensity alone. Its architecture is determined by the geometry of the jet stream and the physics of sinking air. The sun did not bend the jet stream into its omega shape. The total energy the sun provides to Earth fluctuates by only a tiny fraction of a percent over a solar cycle, which is nowhere near enough to cause a regional temperature swing of 12 to 16 degrees above normal. Furthermore, if a brighter sun were the cause, it would heat the entire sunlit side of the planet more or less evenly. It would not create the distinct, alternating bands of record heat and unusual cold that were actually observed. This striped pattern is itself proof that the cause was the jet stream, as only a wave in the atmosphere can produce such a formation. A brighter sun simply makes for a uniformly brighter day. What we witnessed was a wave, and waves are drawn by the atmosphere. It is important to clarify why Calm Space dedicates time to addressing these alternative claims rather than simply dismissing them. Our purpose is not to mock or belittle anyone. Very often, the people asking these questions are simply observing that something extraordinary is happening and are seeking a coherent explanation. They are individuals who may have been let down by media coverage that offers only a simplistic slogan or a dismissive shrug. That impulse, the instinct to demand a genuine explanation, is a valuable one. In fact, it is the very same instinct that fuels scientific inquiry. The objective here is not to tell people to stop asking questions. Rather, it is to walk through each claim with honesty, measure it against the established principles of physics, and see which explanations withstand that rigorous test and which ones do not. When we apply this test, the claim of an engineered heat wave does not hold up. The idea that it was just normal weather also fails. The assertion of faked records does not survive scrutiny, nor does the theory that the sun was responsible. So, what is left? What explanation remains standing when weighed against all the available evidence? The account that this video has carefully constructed is what endures. An explanation that can withstand honest scrutiny is infinitely more valuable than one that merely sounds dramatic. When you clear away the noise of that online weather system, what you find is a story built piece by piece. A distorted and stalled jet stream, an omega block, a high-pressure ridge of near-record strength, and the heat-generating engine of sinking, compressing air. we see three populated regions of the hemisphere trapped under the hot bands of a single atmospheric wave, all amplified by a warmed baseline climate that made such a record-breaking event roughly 3 times more likely. That is what occurred. That is the reality of the situation. And so, we arrive at the question that has been waiting at the conclusion of this entire story. The question itself is rooted in the calendar. Everything described the shattered records, the extreme station highs, the deadly heat on the Indian plains, and the 12 to 1/6 degree anomalies. All of this took place in May. It happened in late spring, a full month or even 2 before the traditional peak of summer heat in the Northern Hemisphere. While the sun is strong in late May, it has not yet reached its maximum intensity. The ground has not yet absorbed the cumulative warmth of June and July. The starting point, the very floor from which this heat dome had to build, was still a spring floor. This leads us to the critical question, one I will leave with you rather than pretending to have an answer for. If a contorted jet stream can lock an omega block over Europe in May, breaking a record that had stood since the World Wars, and do so from a spring baseline, what might that same machinery produce if it forms again in July or August? What happens when the sun is at its most ferocious, when the ground is already hot, and the baseline is a summer floor, not a spring one? An omega block is not exclusively a springtime event. It can manifest at any time. The jet stream can trace that same ominous shape in the deepest heat of summer just as readily as it did this spring. If it does, it will be constructing its dome upon a foundation that is already much, much hotter. Notice that this atmospheric machinery operates without a calendar. This is the quietly unsettling heart of the entire forward-looking question. The omega block has no awareness that it formed in May. The jet stream does not consult the date before it begins to amplify. The physics of the event, the stalling, the high-pressure ridge, the descending and compressing air are identical in July to what they were in May. The only variable that changes between the seasons is the baseline upon which this machinery operates. In the height of summer, that baseline is far higher, influenced by a stronger sun, longer days, and ground that has been absorbing warmth for months. Consequently, the very same atmospheric configuration that broke an 80-year record from a spring baseline would, if dropped into July, be building its dome on a foundation that is already many degrees warmer. The machine is the same. Only the floor under it has been raised, and that is the thought experiment that should stay with you. We have just witnessed the power of this atmospheric system during the traditionally mild beginnings of the warmer months. It raises a sobering question. What might this same system unleash when it forms over the most intense heat of the summer? For generations, we have held a comforting narrative about the seasons, viewing spring as a gentle prelude, a temperate and green interlude before the arrival of summer's full force. But what happens when the atmosphere no longer adheres to that familiar story? It is worth considering whether the distorted jet stream observed this week was not an isolated anomaly, but rather a harbinger, an early glimpse of a new pattern that the remainder of the year may have to contend with. There is a profound thought to consider here. Throughout most of human existence, weather was perceived as an entirely local affair, something happening in one's own valley, one's own town, under the sky one could see with their own eyes. People were experts in their immediate climate, yet knew little of the conditions elsewhere. This recent event, however, demonstrates with exceptional clarity that weather has never been truly local. The heat experienced over Britain, Spain, or northern India was a regional symptom of a vast structure that encircled the entire hemisphere. The same atmospheric river that shaped an afternoon in one location was simultaneously determining the fate of someone 4,000 miles away. For a moment, the curtain was pulled back, revealing the single machine at work, When London surpassed a record from the World War era, Spain approached 101 degrees, and the Indian plains faced deadly conditions, all within days of each other. We in the middle latitudes all live beneath this one connected system, a single, waving, looping river of air that rarely reveals its unified nature so plainly. The title of this analysis suggests that multiple countries are starting to feel it, and that word "starting" is both precise and honest. This was not an event affecting a single nation, but several at once. It did not occur at the height of summer, but on its very threshold. This was not the end of something, but its inception. The heat that shattered Britain's record, baked Spain, and brought tragedy to the plains of India was not a conclusion. It was an opening statement. It was the distorted river of wind, 7 miles above our heads, tracing its first omega pattern of the season, and demonstrating in late May what it is truly capable of. The rest of the year is still ahead, and the jet stream, that silent, invisible, planet-spanning river, has now captured our attention. The only question left is whether we have understood its message, and if we are listening closely enough to be prepared for what it says next.